Thanks for attending my talk. This is about Shoal++. It's a high-throughput DAG-based BFT consensus protocol that offers very low latency and very good robustness. This is a joint work with my colleagues at Aptos Labs, Zekun and Alexander Spiegelman, and our past interns, Florian from Cornell and Sourav from UIUC. So a very high overview of what Shoal++ is. It's a partially synchronous BFT DAG-based consensus protocol. So the assumption is it can tolerate F failures as long as the number of replicas in the system is 3F plus 1. And it works on top of the latest innovations in DAG-based constructions for scalable throughput. And it offers very low end-to-end latency of 4.5 message delays from the transaction origination to the transaction being committed. This is compared to 10.5 message delays in existing state-of-the-art. And it is very robust, being a certified DAG construction. And compared to uncertified DAG approaches that are becoming prevalent recently, it offers very good robustness. So a bit of a background of DAG-based protocols. A few years ago at Erosis, Narwhal was proposed as a means of decoupling data dissemination from total ordering. And this gave Narwhal a huge boost in performance. So Narwhal works as follows. The protocol is divided into a sequence of rounds. And each round, every replica in the system can, in parallel, propose data in terms of directed acyclic graph nodes. And when replicas propose these nodes, they have to link to nodes in the previous round. So they have to make at least supermajority links to nodes in the previous rounds and construct the DAG this way. There is no ordering enforced at this point. This is just data dissemination. And in order to order this DAG, there were other protocols that work completely locally based on the replica's view of the DAG. So there is no communication involved. And protocols like DAGrider, Task, Bullshark, and more recently Shoal have all tried to propose better algorithms to create a total order from this DAG-based view. So, as I said, DAG protocols can scale very good in terms of throughput. So Shoal and Bullshark gave us tens and thousands of TPS, but they were still lacking in terms of latency from leader-based protocols. Leader-based protocols like Joltin had very low latency in our experiments, even sub-second latency. And DAG-based protocols were nowhere close to that. So that is what we try to improve with Shoal++. It's a near optimal latency DAG-based BFT protocol, which reduces the number of message delays to commit from 10.5 to 4.5. And we do this by breaking the end-to-end latency into three main components: queuing latency, anchoring latency, and anchor commit latency. Shoal++ reduces the queuing latency from 1.5 message delays in existing protocols to, just 1 second, 1.5 message delays in existing protocols to a half message delay. And it improves the anchoring latency by trying to get rid of it in most cases. And it works very well in the gracious executions. And it reduces the anchor commit latency from 6 message delays to 4 message delays. So in total, we reduce the end-to-end latency down to 4.5 message delays. The rest of this work, this talk, I'll cover how we reduce queuing latency and anchor commit latency. I'll defer the anchoring latency to the paper. First, queuing latency. So what is queuing latency? This is the latency it takes for a transaction to be included in a DAG node. And to understand how long it takes, we need to understand what goes into constructing this DAG itself, right? So each DAG round involves 3 message delays to add the node into the DAG. So every node goes through a certification process. It's a reliable broadcast-based certification where the replica would take whatever transaction it has and propose it as a node and get votes, signatures from a quorum of replicas and then form a certificate out of those signatures. And this guarantees data availability in the system even if that replica goes down, right? And this takes 3 message delays. Hence, the queuing delay on average, assuming that requests come in uniformly, is 1.5 message delays. Which brings us to our first optimization. Shoal++, more DAGs. Instead of running one single DAG instance, what we do is we instead run 3 DAG instances, each offset by 1 message delay, right? So which means now instead of paying instead of paying 1.5 message delays, transactions now only have to, on average, pay half message delay because there is a node that is created every 1 message delay. And in order to form a total order among these 3 DAGs, we just pick the round robin order. We go from DAG 1, then DAG 2's output, and then DAG 3's output, and so on and so forth. However, it's because the DAG can output different prefixes on different nodes, there are some nuances in ensuring that when we output the total order, we output the same consistent total order between these DAGs on all replicas. And to understand that, we need to revisit the ordering rule that we use in Shoal++, which is same as the bull shark ordering rule. So in bull shark, it divides the DAG view into an anchor round and a vote round. So all the odd number rounds are called anchor rounds, and all the even number rounds are called vote rounds. And in each anchor round, a node is designated as an anchor deterministically by all replicas. This is no communication, just from their local views, deterministically. So in order to commit A1, each replica has to ensure that there are at least F+1 nodes from the next round that refer to A1. Because we built this DAG, and at some point, each node should have references if they had reliably broadcast them properly, right? So in this case, A1 has only 1 vote, so which does not meet the threshold of F+1. In our case, it's 2. So this A1 cannot be ordered. A2 has no references in this case, so it cannot be ordered at all. However, A3 can be ordered because it has more than 2 references. And however, this is called the direct commit rule, but what we can realize is that a different replica could be ordering A1 directly, right? It could have all 3 references in round 2, and it is totally possible. It is outputting A1, but another replica is outputting A3. So how do we avoid this, right? So there is an indirect commit rule in Bullshark that tells us that as soon as we find the directly committed anchor, we need to trace a path through the DAG to find the first anchor that can be indirectly committed. In this case, it's A1, and no other node is going to commit A2 because if one replica does not have any references to it, it is guaranteed that no replica has any references to it. So A1 will be committed first by all replicas and followed by A3. And this offers us a natural switching point for the 3 DAG approach. So whenever A1 gets committed, we can switch over to the next DAG, commit its A1 or whatever anchor it is, and then switch to the 3rd DAG and commit its A1, and so on and so forth. So now next, we'll look at how we reduce the anchor commit latency. So I explained to you what the anchor is about, and in order to commit this anchor, it takes 6 message delays. So where does the 6 message delays come from, right? So in order to add the anchor node into the DAG, takes 3 message delays because the node has to be certified. And in order for all the votes to be certified that refer to this anchor, it takes an additional 3 message delays. And in the normal case, it takes about 6 message delays to commit the anchor. In Shoal++, we introduce a new fast direct commit anchor rule based on the observation that we don't need a certified node to vote for the anchor, but we just need a node that can just refer to the anchor instead. The way we accomplish this is all the replicas would have the node in just 1 message delay, and they don't have to wait 2 more message delay for it to be certified. And as long as A1 has references to 2F+1 nodes in the next round, it can be committed using this new fast direct commit rule. And based on, even if F of them are malicious, because of the reliable broadcast scheme we use, F+1 is guaranteed to be certified and eventually added to the DAG, which would satisfy the old commit rule property. And just to recap, in Shoal++, we reduced the queuing delay from 1.5 message delays to 0.5. And we also looked at how we reduced the anchor commit latency from 6 message delays to 4 message delays. And I would defer the details for anchoring latency to the paper. We evaluated Shoal++ and a bunch of other protocols in a geo-distributed setup. This is similar to those that a lot of blockchains are deployed, albeit not single cloud, but in different cloud. But in our experiment, we ran with 100+ replicas, all distributed in the same Google Cloud, but in different regions, up to 10 regions. And just to give you an idea about what the latency is, the round trip latencies are between any pair of region is between like 25 milliseconds to 300 plus milliseconds. In our comparison, we compared to a leader-based protocol, Jolteon, which is a recent variant of a chain-based consensus protocol. And we also compared with existing Bullshark and Shoal, and also an uncertified DAG called Mysticity. So I didn't explain much about the uncertified DAG, but in a line, it's still a DAG construction, but it just avoids the certification phase of 3 message delays. And that gives it a huge savings in terms of latency. In terms of what we are trying to order, we are just trying to order bytes of transactions that represent a P2P workload in a blockchain. We don't care about execution, so these are just oblivious to consensus. First, we measure the failure-free performance in terms of throughput versus latency. What we found is that Shoal++ gives exceptional throughput up to 1.8 times better than other certified DAG protocols. And it provides 45% better latency than Shoal, and even 60% than Bullshark. And more importantly, we achieved what we wanted to achieve, to provide sub-second latency at scalable TPS, because leader-based protocol like Jolteon already did sub-second latency, but at lower TPS. So Shoal++ is able to achieve sub-second latency at up to 100,000 TPS. And you might be wondering, like, with all the queuing optimizations, how did Shoal++ get faster in terms of throughput, right? And this has to do with our 3 DAG optimization. So instead of producing one node every 3 message delays, we are now producing much smaller nodes every 1 message delay, making better use of our network resources. And that actually helps not just Shoal++ and even Bullshark if we apply the same technique and Shoal in terms of scaling their throughput. We observed that even Shoal++ can reach the, Bullshark or Shoal can reach the same throughput as Shoal++ when we apply the same 3 DAG optimization. Finally, about why we still stick with certified DAGs and we haven't moved to uncertified DAGs. And it's because of the robustness property it provides. And for this experiment, what we did is we ran Shoal++ and Mysticity side by side with each other, and for about 2.5 minutes. And at the 60-second mark here, we started injecting network drops emulating some Byzantine behavior. So what we exactly did was we dropped 1% of messages at exactly 5% of the nodes. And what we noticed is that because the nodes are not certified in uncertified DAGs, they quickly diminish in performance because replicas scramble to find the nodes that are missing. Some have them, some don't, so they scramble to find the missing pieces. But Shoal++, because they're certified, as long as they have the certificate, they can still construct the DAG and fetch the data in the background. So in summary, Shoal++ is a high throughput protocol with up to 140,000 plus TPS. And it has very low sub-second latency, 775 millisecond at 1000 TPS and about 980 millisecond at 100K TPS. And it's also robust under network faults. Thank you.